Alright, welcome to an AQA AS Chemistry video on substitution reactions. So start off the video talking about halogen alkanes, which are the example that you'd use for these substitution reactions. Halogen alkane is a halogenated alkane, as obviously stated in the name, with meaning one or more of the hydrogen atoms in the alkane is replaced by a halogen atom. The names of these halogen alkanes, or the prefix of the name, is determined by the type of halogen that you have. So, for example, I don't know, let's make one up. Let's get this here. Let's make it flora, right? So that would be called then if we're going for the naming of this, we'd just call it a 1 because it's on carbon 1 here. If we're counting from the from the floral, I'll call this the alpha carbon. Call that the alpha carbon. That would be cool. So it's 1, and it's a fluoride, so it would be fluoro. And it's a propyl group, so propane. 1 fluoropropane. And yeah, so the names of halogen alkanes use the halogen. This pretty much all this means that, as I said before, the name could be, if it's a chloro, be chloro, bromo, iodo, etc. Properties of halogen alkanes. Halogen alkanes are polar molecules. It's polar obviously because there's a difference in the electronegativity between the fluoro and the carbon. The polar bonds are important in their reactions, as halogens are more electronegative than carbon. The carbon atoms carry a partial charge, which is, you see this charge. So the carbon atoms, we describe them as being partially positive, and the halogens would be considered as, when they're in the bond, at least partially negative. And halogen alkanes undergo substitution reactions with, for example, the ones you usually see an example are the ammonia, hydroxide ions, and the cyanide ions. So I had this highlighted. Electronegative just means that it usually is a 1 marker in these exams, and ask what's the definition of electronegativity. It's just the ability of the nucleus of an atom to attract a lone pair of electrons in a covalent bond. I feel like I should write that down, but if you really want to go and write that down, just go back in video and then copy it and write it down. But I'll say it again: it's the ability of the nucleus of an atom to attract a lone pair of electrons in a covalent bond. Alright, so nucleophiles and electrophiles, good to just know what they are, because they're pretty much, nucleophiles and electrophiles are just important for not just organic chemistry but understanding inorganic chemistry as well. These are everywhere. A nucleophile is a molecule attracted to a nucleus which is positively charged. Should be saying charged. Let's just get that there. So nucleophiles tend to be negatively charged. So molecules with lone pairs are also called nucleophiles. An electrophile is a molecule attracted to a pair of electrons, or lone pair of electrons, or could be a bonding pair of electrons, which are negatively charged. So that means the electrophiles are themselves positively charged. Nucleophilic substitution reactions with nucleophiles in a nucleophilic substitution reaction. This mechanism is a 1-step process. So let me just go here. I'll show you a mechanism for a nucleophilic substitution with a hydroxide ion. So I'll just show that here. So if I had, for example, I don't know, let's go chloromethane. Chloromethane here. and a H here. So don't worry about that. You have your hydroxide ion here, for example, OH minus, and it's always going from the lone pair of electrons, always going from negative to positive. So this is more partially positive here. So the carbon here, and it'll go from this bond, always going like this. If you don't do it like this, you won't gain marks in the exam, like here. And then when that happens, it creates an intermediate where you have 5 bonds, but obviously carbon only has 4 bonds. This bond here is the best leaving group because it's the most polar. So these are less likely. The hydrogens are less likely to be ejected because this is more. It's just much more electronegative. It's more. This bond is more polar. It's easier for it to. It's an easier leaving group. So always do bond from the bonds. Remember, this is a bond. That's the bond of electrons there. Always from negative to positive. Well, that's not positive, but it's more positive if you're talking about this reaction here. So always going from the bond to the atom, and that's it. That's all it is. My hand probably covered it, but going from the lone pair of electrons to the partially positive carbon atom, then bond to the chloride, and then you have an arrow here to show what the reaction, the final products of the reaction. And it'll be an OH. This isn't a displayed formula, it's a structured formula. And then always show this to show it's gone now. And always put these 2 dots. Always put the 2 dots. Without the 2 dots, you can't show the lone pair of electrons. Yeah, and I can just this whole thing I can do the exact same thing with ammonia. So in case you didn't understand it before, remember it's always from the oxygen in that first example there. The oxygen is the one that's the electronegative. That's where the lone pair come from, not the hydrogen. If you put the bonds here, the lone pairs here, that's wrong. Don't do that because you won't gain the marks from it. And also it's also important to put they're very specific. You gotta have 2 so my hand's covering it here. You gotta have the 2 dots representing your lone pair, and you have to show the negative charge. It's actually on the oxygen, but they will allow if you put on the hydrogen here, just because usually at the end. But you have to have that. You have to have that, and it's always gotta go from the lone pair of electrons to your partially positive carbon atom, and then bond to the chloride. And then when you're representing here, you gotta represent it like that as well. If you don't do it like this, I know it's so they will just literally deduct marks just even for small things like not putting your minus there or your 2 bonding pairs there. These things matter. So yeah, same thing. If I go for ammonia, well, now you guys kind of get, I can go a bit faster. NH3. Let's go for, you could just do the exact same example, it doesn't really matter. Same example here. Here we go. Here. In this case, NH3 in itself isn't that much of it's not actually an ion in itself, and it doesn't require it, but cyanide ions do, but NH3 doesn't require it. But it does have the lone pair represented here. Goes from here to there, and then from bonding pair to chloro here. Now with an amine group is with ammonia, it's a bit different because you're forming when you're doing it with the hydroxide ion, you're forming an alcohol, so you're forming methanol here. When you're doing it with ammonia, you're forming an amine, and you'll see why it does that, because when this happens here, you get this little scenario. You get 1, 2, and 3, but ammonia tends to only likes to form. There are examples of like ammonium salts, but it prefers to have its 3 bonds. You know, it being in group 5 and all. So what it does to do is it loses hydrogen, because this is positive charge here, so it needs to get the electrons here. To get in, it goes from the bond here. It wouldn't go the other way around. The other examples where it goes from here to there, but this is not an example. Otherwise, you end up with a H minus ion, and you don't really want that. You're going, so when that happens, this hydrogen here, it loses that electron, so now you only have H plus now. So now you're left with H plus. Oh, let me just do a little. Now you've lost that hydrogen now, and let's probably just do that there. Try to find some space here. Can I move this down, maybe? Probably, yeah, there you go. Yeah, so, oh, I feel like I messed everything up now. Yeah, okay, I'm just going to do it here. But anyway, the point being, and then you're left with this here, H, that's now an amine group. This here is an amine group. Actually, I can just highlight it, actually. Didn't work out the way I wanted it to, but that part here, this part here, pretty much, that's an amine. Life. Yeah, and then you're left with a Cl minus here and a H plus. I would show it with a cyanide ion as well, but I feel like I don't have any space left. But you know what? Actually, you know what? I will make space. Don't worry about that anymore. Yes, alright, with a cyanide ion, I'm kind of dragging this video on a bit, but hopefully you kind of get the idea of this. It usually comes from hydrogen cyanide, or sorry, potassium cyanide. It's much better at releasing it, but you'll get it like this. And then, I don't know, usually we'll just use the same example. There. And when you do this, you get this little molecule here. Now you could reduce this nitrile into an ammonia, and when you go into year 2 chemistry, this is actually a way of creating ammonia. Sorry, not ammonia. Creating an amine with a high yield. The other wet method that I show you by substitution, you'll see it when you do year 2, but it's less likely to give you an accurate product because you lose the side reactions. But this method here, you don't need to know it as of yet, but it will just create you your nitrile, and you could reduce this in a reaction to get you a nitrile. Sorry, to get you an amine. Sorry. So we're talking about reactivity here. The reactivity of halogen alkanes decreases in order of from iodine. So as you go down the halogen group, it will become the reactivity of halogen alkanes decreases, and that's because the properties of this this is due to the properties of the weak polar CX, should I call it, partial dipole bond. So the CI partial bond is the weakest. So actually, I should have said, as you go down the halogen group, the reactivity between, I have to word this carefully. So the halogen alkane decreases in reactivity in order from iodine, bromine, chlorine, and fluorine. So as you go down the halogens, halogen alkanes, they become more reactive as you go down the group. So iodine, the Ci bond, is the most reactive, and that's because it's a weak polar Ci partial dipole bond, and it's because the iodine is such a bigger atom compared to carbon. As it's bigger as it's a bigger atom and larger and has more electron shells, it means the nuclei of the iodine is further away from the carbon. And when we're talking about the nucleus of an atom being further away from its outermost electron, there's usually a weak electrostatic force of attraction. So, however, when you're talking about fluorine, carbon fluorine, it's less electron shells. I don't remember. I haven't got my periodic table with me, but I forgot how many electrons fluorine has. But it's not many. The point being, so it's because the nucleus is very close to the electron. There's less electron shielding. There's a very strong electrostatic attraction between between the nucleus of the atom of the carbon atom and the bonding pair. So because there's a strong attraction between a CF bond, for example, that means that it means more energy is required to break the bond. So it's a less reactive reaction compared to CI, which requires less energy. So for halogen alkanes to react, the CX bond, X just represents halogens, it needs to break, and meaning that the activation energy is highest for halogen alkane with a CF bond. Therefore, this reaction is the slowest. So hopefully that makes sense to you. And I'll just sum it up basically. The stronger the bond is, the less reactive it is. The more energy needs to go in for the reaction to actually occur. Whereas for a Ci bond, which is it's a very big, there's a very weak attraction between the bond because of the size of the iodine atom. The bond is actually more closer towards the iodine than it is for it's more like, I think it's more like that. It's more like that. It's not in the middle, shared equally. So because of that, the bond is very easy to break, and therefore it's more reactive because there's less of the activation energy needed to break the bond. So if I put an example, so describe and explain. I've put this question, a random question on the side, but describe and explain the speed of the reaction for iodomethane dissolved in hydrochloric acid. In your answer, talk about the reactivity of the halogen alkane and how the reactivity of the iodomethane is related to the speed of the reaction. I'll give you a bit of time. Pause the video now and take a bit of time, not too long, to actually answer the aspects of the question, highlighted the key points of the question, and yeah. All right, I've given you enough time to do that now, so I'm going to go to the answer to it now. So this is a very fast reaction. So if you're describing reaction, it'll be a very fast reaction. That's the describe part of it. And explain, it'll be because, remember the keyword here, because it's showing that you're trying to explain why iodomethane is most reactive halogen alkane out of the whole group, as it requires the lowest activation energy in order to break the CX bond. And that'll be your explanation right there. During substitution reactions, so during substitution reactions of halogen alkanes, the nucleophile attacks a molecule, usually an electrophile, that attacks the molecules and knocks off a halide ion, so a halide atom. So fastest goes over. If I just to give an example of it, as we've just seen before, really, it's nothing really extra compared to what I've just seen it shown before, but it's kicking it off. What I meant by that intermediate before, so I had this example here. Let's go for this again down here. It just doesn't want to work with me sometimes, you know. So, okay, so if I have this here, what's actually happening is that you need to realize is that this is very fastly happening, but you don't really need to understand this for your exam. But I thought, you know, my teacher always told this to me when I was in school. And again, why is it not gonna... Is it gonna do it this way? It's gonna do that way. Okay, good. It's actually you need to realize that what's actually happening here is getting kicked off. It's not like just like it just goes away instantly. We're actually forming here. If I was to take a picture of it, shout out my A-level chemistry teacher, Dr. Bakari. But we're actually forming here. It'll be in 3D space, but let's have that going out there. This is a terrible drawing. Terrible drawing, but you get the picture where I tried to do that. The line should be straight. And then good. And then H here. That's what's actually forming. This is the intermediate that's forming. This, it can't happen because obviously it needs 5 carbons. What it could do is remove this, but then you're back to where you started off again. So, and the hydrogens, this is not a polar bond. It's not going to do it. The hydrogen is not that electronegative. It's not going to, these are not leaving groups. You know, it's not, if a hydrogen was to leave here, it's not significant enough to actually cause, you know, to make it more, to allow the carbon to have, you know, for, you know, it's too electronegative. The carbon wants an environment similar to what it started to with here. If you remove the hydrogen, it's not really going to, this is a much bigger and more polar compound than hydrogen. So removing hydrogen doesn't actually do anything. So what it does, the best leaving group out of these ones, the chlorine. And when that happens, you get your compound here. Now this is just happening, obviously you get your, one thing is like if this was dipped in, for example, hydrochloric acid, and for example when you had like a H plus, one thing you need to know in the exam, and sometimes some people make a mistake of doing it, they put HCl and it looks like it would happen because it's like it's hydrogen and chlorine, and it would just bond together. And I guess they technically would, but you have to remember that, you know, this reaction, this with hydrochloric acid is a very strong acid, so it dissociates in solution fully. You might not know fully that because that's year 2, but you know from GCSE triple, if you did it, that hydrochloric acid dissociates very strongly in solution. That's why it gets like this. So if it did form to HCl, it would just dissociate back out again. So it's best to leave it like this. I don't think they would drop a mark for you if you wrote that in the exam, because technically it's not wrong, but try and just leave it like this, because this is actually very accurate. And this is what's happening. Obviously, so this is what technically happens, but you don't need to show this part. This is just if this was to happen in a split second, this is what actually happens, but it all happens pretty much instantly. And the halogen alkanes are, you know, the three nucleophiles that you usually have for these halogen alkanes when they bind with ammonia, cyanide ions, and hydroxide ions. If it's with a hydroxide ion, you get an alcohol. If it's with ammonia, you'll get an amine. And if it's with a cyanide ion, you produce a nitrile. Let's put nitrile. And then there are other reactions that you could do to this nitrile to convert it into an amine. But you don't need to know that for this video here. And that's it. Hopefully this video was helpful to you. That's it.